All right. All right. You good, Kara? You good, Olivia? We'll go ahead and get started.
Yeah.
All right. So good afternoon, everyone, and welcome to the Professional Development Webinar Series, Strengthening Education and Communication in Vector-borne Diseases, hosted by the VectorED Network, which is a CDC-funded vector-borne disease training and evaluation center. My name is Erica Maxtinger, and I'm from Penn State, and I'm going to be moderating the webinar today along with Olivia Bognani, who is our program manager. If you'd like to know more about the VectorED Network and other programs, evaluations, and trainings we have going on or have upcoming, please do visit our website at vectorednetwork.edu, and we're gonna, .org, and we would put this in the chat. We can't locate our chat, so I do apologize, but we're gonna send these links out with the recording of the video. This series was developed to support professionals like those in extension, public health, education, and all related fields who work to translate science into practice. And we recognize that while many of us have deep subject matter expertise, we don't always have the opportunity to strengthen the communication, design, and evaluation skills that help make our work have the biggest impact. Each month, the series highlights a topic that builds on those applied skills, and we try to have these sessions be practical, resource-heavy, and interactive wherever possible, with examples drawn from vector and vector-borne disease contexts to keep things relevant and real-world. To keep in touch for future events, we do invite you to connect with us on LinkedIn, as well as sign up to receive more information about upcoming events through Penn State Extension and connect with our VectorED newsletter. And again, we will send those links out after the webinar. Let's go here. Please note this session is recorded. That hopefully popped up for everybody. You will receive a link to the recording following the presentation. This webinar will also be posted to YouTube and our website with additional resources linked so you can extend your learning. A few housekeeping items. If you are new to webinars, this session will run for about 60 minutes with roughly about 45 minutes for the presentation. All participants are muted to reduce background noise, but if you experience any audio issues, please check your settings using the arrow next to the microphone icon. You are welcome to post comments or reflections if we can get the chat up when the chat's up. But if you do have a question specifically for the speaker, please use the Q&A feature to make sure it doesn't get lost. Live captions are available. To turn them on, click the CC, which is closed captioning, button on your toolbar. If you need to step away or leave before we wrap up, you can click the Leave button in the lower corner of your screen, and doing so will not interrupt the session for anyone else. And now I'm going to introduce our speaker for today. So Dr. Kara Fickrig is an assistant professor in the entomology department at the Pennsylvania State University. Her research focuses on vector ecology and implications for vector-borne disease epidemiology, with an emphasis on the invasion of Aedes aegypti and dengue to rural areas of the Peruvian Amazon and Aedes albopictus in Pennsylvania. Dr. Fickrig also studies mosquito feeding behavior, a critical component of pathogen transmission cycles. And now I'm going to hand it over to her.
Great. Thank you for the introduction, Erica. And I am very excited to be here today to talk with you all about vector-borne disease epidemiology. Just finished sharing my screen and then I'll get started. Okay. So, as Erica said, my name is Kara Fickrig, and I've been here at Penn State since September. My research is very focused on Aedes-borne diseases, but I'm excited to talk with you about some of the other disease systems as well today. So I've created 4 learning goals for this webinar. First, I'd like you all to understand the core concepts of vector-borne disease transmission cycles by the end of this hour, and recognize how surveillance frameworks operate and how surveillance decisions influence the interpretation of data. I'd also like you to become familiar with U.S. vector systems and their associated pathogen risks, and understand how vector distributions and behavior influence vector-borne disease epidemiology. So a brief outline of today's talk. I'll be starting with some basic principles of transmission cycles, going over some core concepts of vector competence and vectorial capacity, reviewing several surveillance strategies for vector-borne diseases, and then delving into a few examples of vectors and vector-borne diseases in the US context, including West Nile virus, dengue, chikungunya, and Lyme disease. Now, before we get started into more details, I'd like to launch a brief poll. Olivia, I'm not sure if you can help me because I'm not seeing my commands for the polls. A brief poll to get to know you all a little better and understand what your knowledge base is going into this webinar regarding vectors and vector-borne diseases, from nothing, a little, a fair amount, or a lot, and then what field you currently work in. This will help me cater this talk a little bit to your particular backgrounds. Okay. Give it another couple seconds. Most of you responded at this point. Okay. Olivia, would you mind launching the results, please? Or I think I can do it. Okay, here we go. So looks like there's quite a range in terms of background knowledge, but everyone knows at least a little bit about vector-borne diseases, and we have almost half of the attendees who already know a lot. And then we have representation from extension, public health, outreach, academia, and other fields as well. So we have a great spread here. So hopefully what I'll be sharing for the rest of this hour will help people across all of these different knowledge levels and job types. So back into this. So to review some basic concepts to make sure that we're all on the same page as we talk about vector-borne diseases, there's a few types of transmission cycles that I'd like everyone to be familiar with. So the first term that I'll review is enzootic, which describes a disease that is constantly present in a non-human animal population in a given location. So an example of this is the enzootic part of the transmission cycle of West Nile virus, in which the virus is transmitted between birds by mosquitoes in a cycle. A zoonosis is a disease that can be transmitted to humans from non-human animals. And so West Nile virus is considered a zoonosis because a mosquito can bite an infected bird and then act as a bridge vector and bite a human and infect that human. This is a zoonotic disease. There are other animals as well that can be infected in the West Nile virus transmission cycle, such as horses. And it's important to note that both horses and humans in this transmission cycle are dead-end hosts, meaning once these hosts are infected, they do not mount a viremia sufficient to be able to infect a mosquito that then bites those hosts. So the onward transmission cycle is really focused in this mosquito-bird cycle. We also have anthroponoses. These are diseases that can be transmitted from human to human by a vector. An example of this is dengue virus, in which the virus is transmitted between humans by mosquitoes, and primarily Aedes aegypti, as well as Aedes albopictus mosquitoes. And in all of these cases, when we use these terms to refer to vector-borne disease transmission cycles, vectors are the mode of transition between the individuals, whether it be an enzootic disease, a zoonosis, or an anthroponosis. So a key concept in vector-borne disease epidemiology is vector competence, and this is describes the ability of an arthropod to become infected with and transmit a pathogen or parasite. So this term can be quantified, so this concept can be quantified as the proportion of exposed vector individuals that become infected and develop a disseminated infection and ultimately go on to transmit a pathogen. And so vector competence can vary a lot in the relationships between different vector species and pathogens because of a number of different barriers that the pathogen experiences once a vector is exposed. So in the instance of a mosquito, the mosquito takes a blood meal, the blood enters the midgut along with the pathogen if the host is infected. That pathogen then experiences a number of different barriers in the midgut, including the basal lamina, permeability, digestive enzymes in the peritrophic matrix, and different microbial interactions within the midgut. If a pathogen is able to escape the midgut, despite all of these barriers, it then enters the hemocell of the mosquito and encounters the cellular immunity. And then eventually the pathogen has to make its way to the salivary glands and enter these glands to be able to then go on and infect another host because the mosquito, when it then bites another animal, will inject its saliva as it's pumping up the blood. And so in order to infect a host, the pathogen must be in the saliva upon that subsequent feeding. And so all of these barriers determine whether a vector is able to transmit a given pathogen. And so it becomes a very specific relationship between a pathogen and a vector to be able to pass all of these different barriers. And there's a number of different ways that we measure vector competence through assays in the laboratory. And so one example of this is shown in this picture. So in this case, the mosquito was exposed to a pathogen, probably in an infected blood meal, but there's also instances where the pathogen can be injected directly into the body of the insect. And then the mosquito is prompted to salivate into this capillary tube by inserting the proboscis in there. And the contents of the capillary tube can be analyzed to determine whether a pathogen was ejected along with the saliva from that mosquito. So this is one way of showing that that pathogen was able to make it all the way to the salivary glands and thereby expose a potential host through this kind of biting behavior. However, it's not the perfect measure of vector competence because it doesn't show that next step of actually infecting a host. And so in an ideal scenario, if a model system exists, there would actually be a test to see whether that mosquito is able to infect an uninfected host. But that we don't have these kind of model systems for all pathogens. Now I'm going to get into like a little bit of detail here, but don't be overwhelmed by seeing the equation. I won't focus on the math too much. This is the vectorial capacity equation. This is a very core concept in vector-borne disease epidemiology. In this case, in this equation, C stands for the number of potential infective bites received daily by a single host, assuming a totally susceptible host population. So for those of you who work in other areas of epidemiology, this may sound somewhat similar to the basic reproductive rate or are not. It's a very similar concept. In this case, because of the complexity of vector-borne diseases, there's a number of different variables that integrate into determining the actual ability of a vector to transmit a pathogen in the real world, regardless of whether it's extremely competent or not. So one of these variables is the density of the vectors in relation to the density of host. And so this can be determined, for example, by different mosquito or tick surveillance methods. And then we have A, which is the human biting rate, which is the number of human blood meals per vector per day. So this is the actual contact between a vector and the host of interest. Vector competence is that concept that we just went over in terms of the actual ability of a vector to acquire and infect a host with a pathogen. P is the daily probability of mosquito survival, and N is the extrinsic incubation period, which is the time that a pathogen takes from the point at which a vector consumes the blood meal, the infected blood meal, until it's able to infect another host when that pathogen enters into the salivary glands. And so I'd like to pause for a moment of reflection and ask you all which variable has the largest impact on vectorial capacity. Olivia, if you could launch the poll for this question, please. We'll take a few seconds here. Your answers could include the density of vectors, the human biting rate, vector competence, probability of mosquito survival, or the extrinsic incubation period. Okay. Looks like the majority of people we'll give you a few more seconds. People are still answering. right. So, the answers really run the gamut here, though most people have said the vector competence as the answer. In fact, the variable that has the largest impact on vectorial capacity is the daily probability of mosquito survival. You can see that P here, the daily probability of mosquito survival, appears twice and has an exponent here in the upper side of the equation. A mosquito's survival is extremely important in determining its ability to transmit a pathogen because it must first live long enough to bite a host that's infected and then live through that extrinsic incubation period where it becomes infectious and then bite another host. And so the survival is a really key aspect of this. And another very important variable after the probability of survival is the human blood meals per vector per day, shown here in A, which you can see is squared. So the contact between a vector and a host is extremely important in determining whether that mosquito is ever able to transmit the pathogen. All right, moving on. So that equation that I showed you for vectorial capacity is one of the most simple versions of that equation that exist. It's been varied often by different scientists with different iterations of complexity. So, for example, there has been a group that has created a temperature-sensitive vectorial capacity model where all of these variables that have the T after them are able to fluctuate as a function of temperature, which is more realistic in a real-world setting. There's also a variation of vectorial capacity in which the probability of survival is allowed to change by age, called age-dependent mortality. So if you think about humans, as we get older, our probability of dying increases as we get older. That's also the case for mosquitoes. And so it's a much more realistic scenario to allow that probability of survival to vary with the age of the mosquito. So there are 4 types of vector and vector-borne disease surveillance that I'd like to mention. First, the human case surveillance. Second, animal or sentinel surveillance. Third, vector surveillance and pathogen testing. And third and fourth, though I won't be concentrating on it in more detail, is community science surveillance, which can also be very valuable. But I'm going to go into more detail on these first 3. So to begin with, human case surveillance. This is a measure of reported human infections, and this can include either confirmed or probable cases. And this directly tracks disease burden, identifies outbreaks when they're happening, and can support public health response to these outbreaks. So this is a very valuable type of surveillance, but it does have a variety of limitations. First of all, it starts to alert of the instance of cases after transmission is already at high levels. And so for many of these diseases, transmission is picking up in the mosquito and host reservoir and starts to increase before it ever spills over to humans. And so this is a relatively late warning. We also know that underreporting is very common for the majority of diseases. Many vector-borne diseases have a variety of different symptoms that they can cause in humans, ranging from asymptomatic or no symptoms all the way through very serious manifestations. So most people won't go to the doctor for a simple fever. And so there are often cases of vector-borne diseases that go entirely unnoticed because people simply are not going to the doctor for diagnosis. And then also, the doctors don't always turn towards vector-borne diseases as the potential explanation for those instances of febrile cases. And even when they do, sometimes there's a lack of reporting, especially if the disease is not a reportable disease, and so that may not be captured by state or national surveillance systems. There's also diagnostic limitations. So the tests that we use for many vector-borne diseases are not perfect. There are issues with sensitivity or specificity. So an example of this is dengue and Zika viruses have a lot of cross-reactivity. And so, for example, a person may have been actually infected with Zika virus, but if they take a dengue test, that may be positive because of that cross-reactivity. Another type of surveillance is animal or sentinel surveillance, and this measures the infection or seroconversion in animals. So this can encompass purposeful sentinel animals, which are, for example, here's a flock of sentinel chickens at the San Mateo Mosquito and Vector Control District. So these mosquitoes are allowed to exist in the environment where mosquitoes also naturally occur, and the Vector Control District will periodically test these chickens for seroconversion, meaning that they're looking for antibodies for the West Nile virus. And so if a chicken is to start out without antibodies and then at some point in this surveillance period turns positive, that's an indication that that chicken was infected with West Nile virus at some point between those blood draws and would signal that there's transmission ongoing in the area. We can also use notable illness or death in natural animal populations. So an example of this is the dead bird surveillance that occurs for West Nile virus. So many vector control counties or state health departments will accept reports of dead birds, and in some cases they will test those dead birds for West Nile virus to determine whether that death was associated with infection. And so peaks in the instance of dead birds occurring with positive tests for West Nile virus can signal that West Nile virus transmission is occurring in the area. We can also harness veterinary reporting systems. So, for example, horse cases of West Nile virus or Eastern equine encephalitis can also signal transmission is occurring in an area. So these can be very cost-effective early warning systems. But it's important to note that they do not necessarily measure human exposure directly. So depending on where the humans are occurring in relation to where the animals are, or different biting patterns of the mosquitoes in the area, there may be disproportionate exposure of the animals to these pathogens compared to humans. And so when we talk about animals, naturally occurring domestic or wild animals or sentinel animal cases of disease, it's really important to distinguish that this is not a direct measure of human exposure, but rather an early warning that transmission is occurring in the area, potentially flagging increased risk. Another type of surveillance is direct vector surveillance and pathogen testing of those vectors. So this type of surveillance measures the presence, abundance, species composition, and infection status of vectors. This can also serve as an early warning before human cases emerge. And it can have other benefits as well, like identifying high-risk species. So although different vectors may be, as we mentioned, competent for a specific pathogen, we might find that certain species are more likely to be infected because of those other dynamics that occur, like feeding patterns, and can help us to understand which of these vectors are the highest risk, which will allow us to target our vector control to those high-risk vectors by targeting, for example, their particular larval habitats or areas where their distribution, where their abundance is higher. And this vector surveillance can also be used to assess the efficacy of vector control. So in the instance of increased risk, oftentimes vector control districts will use, for example, a type of insecticide or other control measure in a given area. And so the ongoing surveillance can allow us to determine whether that control activity led to a decrease in the abundance and the infection rate of the vectors that are being encountered in the area. There are a number of limitations to this surveillance mechanism as well. It's very resource intensive. So a high quality vector surveillance system involves a lot of traps distributed over a wide area and over the entire season. And so this requires a fair amount of personnel time and therefore also financial resources. And so because of that, sometimes because the resources are not sufficient for a very high level of coverage, um, one of the ways to compensate for that is to reduce the number of traps that are operated, thereby also reducing the number of mosquitoes that have to be identified and tested afterwards. And so this can lead to very patchy or seasonal data, which can complicate our interpretation of the data and also lead to some blind spots. Um, and different and there's also different types of traps and other things involved in surveillance that can influence the interpretation of the data, which I'll get into in a moment. Just like to share a couple maps here. This is from the VectorServe database. The top map here shows data that's been shared with this database from a variety of state and county vector control programs, and the counties are colored by the infestation status of the invasive species Aedes albopictus, which is a vector of over 20 different pathogens, including dengue, Zika, and chikungunya. And so you'll see that not all of the country is filled in. That's because the reporting to this particular database is patchy based on the district. But key to interpreting this map is that you can't make any kind of determination about the areas where there's no data filled in. So just because a state might be entirely blank doesn't mean that the species isn't there, but rather that the data from that area is not reported into this database. VectorServe also has a great system for showing the positive instances of mosquitoes and sentinel animals and dead birds for West Nile virus, and as well as positive mosquitoes for uh, other viruses. And so here on the map of California, you can see points that show these different instances of positive collections. And that can help to show a potential risk in these areas for the different pathogens that VectorServe is reporting on. So surveillance data is highly influenced by the type of surveillance that's conducted in terms of the trapping strategies that are used. These three images show three of many of the different mosquito traps that are available for mosquito collection. The leftmost trap here is the CDC light trap. This is typically operated overnight. It uses a light to attract the mosquitoes, and it has a fan here. So as the mosquitoes are attracted to the light, they're sucked in and then kept in this bag. So in the morning when the field personnel come, they are able to take the bag off of this apparatus, close it, and then those mosquitoes are transported back to the lab for identification and pathogen testing. These types of traps tend to be better at collecting night active mosquitoes because, well, for one, they're often operated overnight, and also they harness that light attraction, which doesn't necessarily work for all mosquitoes. So another option is the BG Sentinel trap. This model was specifically designed to attract Aedes aegypti and Aedes albopictus mosquitoes. It often is paired with a human-scented lure, and so the mosquitoes are attracted to that scent, and then attracted at close range to this contrasting color between the white and the black, and then they're sucked in through a fan and then kept in a baggie on the inside of this apparatus. And again, the field personnel will come, take that bag, and then bring it back for later identification. Another trap type is the CDC gravid trap. This harnesses the egg-laying behavior of mosquitoes. So this black tub contains water, typically treated with some sort of infusion of an organic material, often hay, that's been allowed to ferment for a period of time. And then that fermented organic material lets off an odor, which doesn't smell very good, but the mosquitoes love it, and they're attracted to this water to lay their eggs. And as they come into the tub, they're sucked up again by a fan and then kept in this container until the field personnel come to collect. Another type of surveillance that does not rely on traps, but rather active observation, are larval surveys. This is a very common surveillance method, especially in areas of South and Central America where dengue virus is endemic, because this is the typical way of looking for Aedes Aegypti habitats. And so here you can see a field employee collecting larvae from a tire using a turkey baster. And so often surveillance data from these types of surveillance methods will show the proportion of houses that were positive for containers, for larvae positive containers, and other types of ratios that show the infestation levels of Aedes mosquitoes in the area that was surveyed. So, as I mentioned, through most of these surveillance methods, the mosquitoes are collected and brought back to the lab for identification. Once those mosquitoes are speciated or identified to species, they are then pooled for pathogen testing. The reason that mosquitoes are pooled, meaning grouped into a greater number of mosquitoes than just one, is because infection rates are relatively low. And so if we were to perform PCR on every single mosquito to try to determine whether it's positive would be incredibly time and resource intensive for very minimal positive hits. And so the mosquitoes are grouped and then tested in these groups or pools. Using the data that comes out of those pools, we calculate the minimum infection rate, or MIR. This is calculated by the number of positive pools divided by the total specimens tested, multiplied by 1,000. So the result is the number of infected mosquitoes per 1,000 mosquitoes tested. So this minimum infection rate assumes that there's only one mosquito that's positive in a given pool, which is a very conservative estimate and can lead to inaccuracies if infection rates are high. So there are alternative methods for reporting results. For example, Bayesian estimates of individual infection probability. So depending on the scenario, minimum infection rate may lead to an underestimate of the actual infection rate in the population. Now I'd like to introduce you all to a very valuable resource called ArboNet, which is managed by the Center for Disease Control. It tracks a series of mosquito-borne diseases, which are listed here. And I'm just going to bring you through how to navigate this platform for the example of Eastern equine encephalitis. So I'm going to try to play this video here. And you see this is the ArboNet home base. You can click on the disease of interest, go to data and maps there. And if you're interested in seeing historic data, you can click on the historic data. This is showing data from 2003 to 2024. You can see different case reports over this time period, over different types of stratification, as well as maps of the disease across the United States. And then they're interactive. So here, for example, you can click on Pennsylvania and you can see the reports for different counties within Pennsylvania as you highlight over them. And so the different colors on the map represent the lighter kind of turquoise is non-human activity, so that might be positive mosquitoes or animals. The medium blue is human disease cases, and then the darker blue shows both non-human activity and human disease cases. The takeaway message from this section is that there's no single surveillance system that really tells the whole story of what's going on in vector-borne diseases. Each surveillance system has its biases and limitations unique to the system. Some strategies provide early warning, while others may trigger the alarm too late to effectively implement vector control. Some strategies are also a direct measurement of human burden, while others just indicate risk in the environment. And so as we look at the data that comes out of these surveillance systems, it's really important to understand the detail of how the surveillance system was designed. For example, if it's a vector surveillance system, what types of traps were used and what type of biases those might have, or the degree to which human cases are reported, and how it's really important to understand all of the details so that we can effectively communicate the implications of that data correctly without triggering undue alarm in the case of kind of for example, positive mosquitoes, while also making sure that people are protecting themselves when there's increased transmission. So with all of that background-based knowledge, I'd like to go over a couple examples of US vectors and pathogens. This is by no means going to be an exhaustive summary of all of the vector systems in the United States because I don't have enough time, but I'd like to use these examples to highlight how important it is to really understand the details of the surveillance data in interpreting that data. So first, I'll talk about the West Nile virus system. Here, these three maps show the spread of West Nile virus from 1999 through 2004. And so you can see this really massive explosion of West Nile virus transmission across the country from its original introduction to the United States and its quick spread throughout. And this map here on the left shows the case, the non-human activity as well as human infections across the country in 2024. So notably, this pathogen is transmitted by multiple different Culex species, and the predominant vector species, or the most important vector species, does vary by region in the United States. So in the north, it tends to be Culex pipiens, in the south, Culex quincunfasciatus, and in the west of the Mississippi, Culex tarsalis. And so kind of an important overarching aspect of these Culex mosquitoes is that they can have differences in their larval habitats, but all three of these have been associated, for example, with water in storm drain systems. So I'd like to pause here and ask you all to reflect on whether you think drought or high rainfall might increase the West Nile virus infection rate of mosquitoes. So this poll should have opened for you all, so please pick whether you think drought or high rainfall is more likely to increase the infection rate. All right. Um, a 32% say drought and 68% say high rainfall. Let's see, sharing the results there. You can see there's folks who believe it may be drought, and slightly more people believe it to be high rainfall. Now, interestingly, this was a bit of a trick question because I talked about the mosquitoes using storm drains as their larval habitat, but oops, this is actually a kind of unexpected relationship in which drought can increase the infection rate of West Nile virus. And so this is because, again, vector-borne diseases are very complicated and involve all sorts of different moving parts in the environment. So while drought will actually decrease the mosquito abundance because there won't be as many larval habitats for the mosquitoes, it actually increases the contact between the mosquitoes and the bird reservoirs because there's more limited water resources. And so there's this kind of concentration of both the birds and the mosquitoes at more limited water sources, and this increases that contact or the feeding between the mosquitoes on the birds. And this can actually, although the abundance of the mosquito decreases, the infection rate increases, and this can increase the risk of West Nile virus in a drought situation. So when thinking about mosquito-borne diseases, sometimes we have to kind of think about all of these complexities and not take the first knee-jerk reaction of what seems like it makes the most sense, right? Like lots of water, lots of larval habitats, lots of mosquitoes. You might think also a lot of mosquito-borne disease, which is often the case. But in the case of West Nile virus, because of this bird-vector contact change, there's this paradoxical relationship. Okay, now moving to a different disease system, we'll discuss briefly dengue in the Americas. This virus is transmitted predominantly by Aedes aegypti, and a secondary vector is Aedes albopictus. And this graph is from PAHO, the Pan American Health Organization, and it shows the suspected dengue cases reported since 1980 all the way through 2025. And you can see this increase over time in the number of dengue cases in the Americas with this massive record-breaking peak of cases in 2024. And so that peak in dengue virus cases across the Americas also led to a lot of dengue action in the United States through travel-associated dengue cases. So here you can see that same peak in 2024. This is travelers returning to the United States infected with dengue virus. And this is an important example of how viruses do not necessarily respect borders and will travel between countries because of how highly mobile the world's population is. And so because there were many instances of travel associated dengue cases arriving, this also, of course, increases the risk that at some point in time that might establish some local transmission. And so again, you can see, although not as high as in years prior, in the early 2010s, you do see this peak in 2024. These maps show the dengue cases in 2025, and you can see on the top travel associated and on the bottom the locally acquired in California, Arizona, and Florida, as well as in a number of the US territories. So when we are discussing dengue cases in the United States, it's really important to differentiate between travel-associated dengue and locally acquired dengue. And a little bit of an anecdote here. In 2024, New York experienced record-breaking number of travel-associated dengue cases, which started to get picked up in the media. And at the time, I was working at Cornell as a postdoc on Aedes aegypti and dengue. And so I was interviewed by a local news outlet. That was very concerned about this record-breaking number of dengue cases. And throughout the interview, I really tried to emphasize that these were all, up until that point, travel associated, and that that is, of course, concerning because it leads to the risk that there might be local transmission following the introduction of the virus, but that it needs to be understood that these cases are because of travelers coming in infected. And that highlights the kind of interconnectedness of risk around the world. But just a word of caution, when I later watched the interview that I had done with that news outlet, they did kind of cut out many of the places where I was emphasizing that caveat that these are all travel associated. So for those of you who do interact with the media, just make sure that you're always returning to your core message and repeating it often enough that no matter how it's parsed, your core message comes through. That in this case, my core message, and I probably should have continued to repeat even more, that these were travel associated dengue cases. Now shifting again to another disease system. This is chikungunya, and here on the right side you can see a map from Europe reported by the European Center for Disease Prevention and Control, and it shows the locally transmitted chikungunya cases in 2025. There were 788 locally acquired chikungunya cases in France and 384 in Italy, which was a record-breaking number for Europe. Now, chikungunya virus is another virus that is transmitted by Aedes aegypti and Aedes albopictus mosquitoes. In the US in 2025, we only had one locally acquired case, and that was in New York. And the most we've ever reported was 12 locally acquired cases back in 2014, which was when there was a very large epidemic throughout much of the Americas when chikungunya was first introduced to the Americas. Now, only one locally acquired case is much lower than what we're seeing in Europe, and what we saw in Europe in 2025. And this is despite the fact that the competent vector for chikungunya, Aedes albopictus, is present throughout much of the country, as well as Aedes aegypti in parts of the country. This map here is from the VectorServe database that I introduced you to earlier, and it shows a map of New Jersey and Long Island and New York. And you can see the map is colored red for the counties that are positive for Aedes albopictus presence and gray for those that have not yet reported the presence of the species. This is the species is very widespread, and as someone who's worked on Long Island on this species, I can tell you firsthand that it's in great abundance on Long Island, to the point that people will even avoid going outside because they really don't want to get bitten. They're incredibly aggressive biters that bite predominantly during the day. So I'd like you all to reflect for a moment. What might be the difference between the situation in France and Italy, where there's such high levels of chikungunya transmission in 2025, and the situation in the US that would explain the difference in this reported case burden? So if you could all take a moment, we're opening an open-ended poll here. You can just type in what you think might be leading to these differences in these two different areas of the world. And these are anonymous, so no worries, just type in whatever comes to mind. We'll wait for a couple more answers here. All right, let's see what people think. Let's see, share results. Can we see the, or, okay. Not sure if I can, oh well, I thought I'd be able to see people's answers. Olivia, I'm not sure if you're able to see people's answers or if it's just because of how I'm in.
Yes, so we have travel, marketing to the websites to report cases, differences in temperatures and seasonality, less severe winters in the Mediterranean, lack of vector control of mosquitoes, population and weather dynamics, and let's see, more coastal regions in European countries, environment or climate, and also screening.
Awesome. Thank you for reviewing those results, Olivia, and thank you for everyone who gave your guess. I'll say there isn't necessarily one right answer to this. This is kind of hypothetical still at this point, but I'd like to share with you all my pet hypothesis, which is the difference in blood feeding patterns of Aedes albopictus in these two countries. So in the United States, people often live in relatively cloistered environments with air conditioning and window screens, really inhibiting that contact between the vector and humans. Whereas in France and Italy, people often live with more open windows, without screens on all their windows, and often without air conditioning, at least to the extent that we use it in the United States. And so this really changes that that host contact interface between the mosquitoes and the humans. And so studies have been conducted on the blood meals of Aedes albopictus in Europe and in the United States. So scientists will go out, collect mosquitoes that have blood in their abdomen, and then they can look at the DNA in that blood to figure out which animal it came from. And in many European countries, we see relatively higher levels of human feeding compared to in the United States, where the mosquito tends to feed more on other types of animals. And so this really inhibits that ability for the virus to take off in a transmission cycle that hops between human to human by the mosquitoes, because often that feeding train is blocked by feeding on a different animal. So even if Aedes albopictus were to feed on an infected traveler that came in with chikungunya, if it then feeds on a dog afterwards, there's no onward transmission in the human population. Whereas that was more likely to happen in France and Italy. And as somebody who often concentrates um, on vector feeding dynamics, I really believe that this is a key part of the difference in these two scenarios. There's probably also other differences that were noted by the participants that may also play a role. But this is kind of, I think, a dynamic that needs to be further teased out. Okay, for my final example, I'm going to be switching vectors over to ticks. This map shows the distribution of tick-borne diseases in the US between 2019 to 2022. Each of the dots is colored by a different type of tick-borne disease. You can see the distribution of those diseases by the points and colors in the legend down here. This is from the Center for Disease Control. But in this case, I'm just going to concentrate on Lyme disease cases. On the left side of the screen here, you can see the distribution of Lyme disease cases in 1995, relatively limited to the Midwest a little bit, mostly here in the Northeast. And then in 2023, where these two foci have expanded in the Midwest and the Northeast, and we see more instances of cases throughout the US, but still really focused in these two areas. If we look at the Ixodes scapularis distribution, this is the deer tick, the main vector of Lyme disease in the United States. And you can see in red are counties that meet the criteria for an established population of Ixodes scapularis, and the yellow colors show the projected suitable habitat for black-legged ticks based on models. And so you'll see that there's quite a bit of overlap between this 2023 map and the distribution here, but not exactly. We see cases spread throughout areas where the distribution of Ixodes scapularis is not currently or not predicted to be. And we also see some areas where Ixodes scapularis appears to be very established, and yet we don't see that same level of Lyme disease burden. So I would like to take another moment of reflection, one more poll, and ask you, why don't these maps align perfectly? Again, this is a short answer, open-ended question. You could just take a little bit of time to put in your guess here in the short answer. Again, anonymous, so please don't hesitate. Take a wild guess, even if you're not sure. All right, if you have your message mostly formulated, press enter because we'll end the poll now. All right, Olivia, any answers of note?
I tried sharing it. Let me know if you can see or not, but I can read them aloud.
Okay.
Transmission dynamics are different, also temperature. Let's see, scapularis isn't the only tick that can transmit Lyme, ? Whether various agencies report or not. Both are tick-borne. Travel, varying animal populations, outdoor recreation hotspots, host preferences and feeding behavior, diagnosis biases, pathogen reservoir differences geographically. Then ticks behave differently in the north versus the south.
Okay, great. Thank you, Olivia. All right. I heard in that list two of the answers that I'd like to share with you. So one of the reasons that there's not a perfect overlap is because there is another vector in play. Here you can see Ixodes pacificus, which is the primary vector on the west coast. So you can see its distribution shown on this map. And another explanation is that Ixodes scapularis feeding behavior varies across the eastern part of the country. So in the south, Ixodes scapularis tends to feed often on lizards, which are a poor reservoir for Lyme disease. And so this leads to differences in the questing height. Questing is where the tick goes to the edge of the upper edge of the vegetation, typically in the north, and then waits to grab on with its front legs onto a passing host. And so in the south, they tend to quest lower and don't as often attach to humans. And then also they have lower infection rates in the nymphal stage because they are feeding more often on lizards as larvae, whereas in the north, they're feeding often on mice and other better Lyme disease reservoirs, which leads to higher infection rate of those ticks. This is a graph of the reported Lyme disease cases in the US, and you can see here in 2022, there's this big jump in Lyme disease cases. And so just looking at this graph, you might think like, wow, Lyme disease has really exploded all of a sudden in the past few years. But it's important here to consider the differences in the case definition over this period of time. You can see by color 3 different case definitions that have been used to lead to a Lyme disease report. So in 2022, the reporting system allowed for a modified 2-tier testing system, which allows for the faster ELISA test to be used rather than just the immunoblot. And so because of this change, it led to a much greater number of Lyme disease cases being reported, not necessarily that there was an increase in the actual number of cases. And so when there are these changes in reporting systems, it can become difficult to compare the data from before to after to know really the comparison between the two. So it's really important to take into consideration differences in disease reporting during the time period you're interested in. So these have just been a few examples of vector-borne disease systems in the US, but I hope they have got you to think about how vector distributions and vector behavior influence epidemiology and how surveillance and case reporting systems influence the type of data that we receive, and the importance, finally, of thinking critically about how to interpret that data. So as we translate this information for more actionable education, it's important to consider using messaging that center on the behaviors you want to change. So not just saying, prevalence change from X to Y, but rather that, for example, infection levels are very high this spring. So it's especially important to perform tick checks now. Also important to change technical terms for more relatable language, like we might use ability to spread disease instead of vector competence, and always to translate risk levels into clear actions, again, circling back to that behavior. And always anticipate potential misinterpretations. Like, for example, if you say there's no reported cases, people might think there's no risk, but that's not necessarily true. And so with those last messages, I'd like to thank you all for your attention, and I'd be happy to accept any questions. And I believe Erica has a few closing messages for everybody before we wrap this webinar up. So thank you all for your time today.
Awesome. Thank you so much, Kara. I am going to try and do this share again with this crazy screen. All right, there we go. So we are going to finish up with a few things before we get to the Q&A. I just want everyone, just a quick note that this presentation is for educational purposes only and is not intended to be a substitute for veterinary or medical advice. I do want to make sure everyone knows about our next webinar in this series. We're excited to have Dr. Peter Winch, who's a physician from the Johns Hopkins Bloomsburg School of Public Health, coming to talk to us about facilitating behavior change conversations. This will be April 16th at 2 p.m. Eastern Time. You can register for that webinar by using the QR code on the slide or going to the web address listed. And these links can also be found on our LinkedIn page and the VectorED Network website. We also invite you to sign up for a monthly newsletter, as I mentioned in the beginning, that provides updates on these trainings, on jobs, on new information on vectors and vector-borne diseases, and to access past recordings of this webinar series. And you can use these QR codes or the web links to find this information, or again, it is available on our website. And finally, I'm going to ask one more thing of all of you, and that is to do a short evaluation of this presentation so we can continue to get better. So you can use this QR code. You'll also be prompted, I hope, at the end of this evaluation, or to do the evaluation once you close down from Zoom. Again, thank you very much, everybody, for your participation and interest in this webinar. And I am now going to open the floor for questions. Please remember to put them in the Q&A box since our chat disappeared. We're unable to, oh, there we go. And Olivia has put all those resources we talked about, the links that we mentioned that we were not able to put into the chat, into a poll. So you guys should be able to copy those and have access to them at least one way. There we go. All right.
One question from Josefina. Can weight for increasing distribution for the future? Josefina, do you mind clarifying a little? Were you talking about Lyme disease there? And not, if you could give a little bit more information about your question, that'll help me.
She says yes.
Okay.
Yes, Lyme disease.
Okay. But waiting for the increasing distribution. So it's like the Ixodes scapularis distribution may change going into the future, and so that may also change the distribution of Lyme disease. And I also believe that there has been some movement, my understanding of this different feeding behavior from the north moving further south, and so that may also begin to expand Lyme disease risk further south. I see another question. How can educators stay abreast on the numerous updates in the vector-borne disease world, news coverage, publications, scientific breakthroughs, while avoiding information overload or burnout? That is a great question. So for like breaking news, I would say there's PubMed releases that can tell you about different outbreaks as they're happening, but you get a lot of emails from that. So that might be, that might go more towards the overload burnout. Perhaps periodically checking some of these different databases that are linked in the resources may be one way, or following the centers of excellence and like, for example, VectorED, the Center for Disease Control has been funding various centers by region of the United States. And so those can be great resources for timely information that are pertinent to the United States.
I'm going to also add in, Kara, just a shameless plug for extension. A lot of extensions will have an entomologist or at least a vector adjacent person that you can reach out to who may be able to help you kind of condense, like, what are the hot things I need to know right now, so you don't have to do all the work. They're the ones kind of doing that and keeping up to date. So a lot of them are starting to get vector folks or have expertise in vector-borne disease. So don't exclude extension as a resource.
Great plug, Erica. Yeah, that sounds nice to have someone do all that work for you. That would definitely avoid burnout. Any other questions from the audience? I realize we're over time, so thank you for everyone who was able to stay for the hour, but I'm happy to stay on and answer questions if anyone has more. Oh, I see some down. Oh, sorry. And Josephina also said that it's interesting how pathogens interact with biodiversity, which is, yeah, a very good point. The host populations can really influence the feeding behavior and the probability that a vector will pick up the pathogen from a given host. So this is definitely a good observation.
Super. So for folks still on, feel free to continue adding questions for another couple minutes, but do want to ask you all again. Oh, we have one more question. I'm going to ask you all again to please fill out the evaluation. If you have a second, it's only a handful of questions, and there's one question about what you want to see us present on next. So please go ahead and do that. So Kara, this other question is, can you speak at all on how vector-borne disease transmission functions in urban settings? I'm specifically interested in if urban settings mimic the relationship between vector-borne disease and resource availability illustrated by the West Nile virus drought example.
It's a really interesting question. I think the answer probably depends a lot on which vector-borne disease system we're talking about and which urban area. Urban cities in different areas have very different characteristics. So the disease kind of transmission cycle that I'm most familiar with are the Aedes-borne diseases. And so in that situation, the more kind of container filled with water will lead to higher levels of mosquitoes, and then we also typically will see a peak in the transmission with the rainy season as more Aedes aegypti or Aedes albopictus are produced in the environment because of this increase in the vector habitats. So depending on the particular scenario, that it wouldn't necessarily follow the same relationship as with West Nile virus drought. And also, I mean, if we're thinking about that particular relationship, that was a lot driven by the host contact. And so there might be some other way of thinking about something that happens in an urban area that would influence whether people are exposed to mosquitoes other than just the larval habitats in the area. Nothing's coming to mind at the moment, but people who are familiar with different urban areas around the world might think of something like differences in how people open their windows at different points of the year, or something in that regard.
Great. Okay. So this is the responses from Mel K. It says, William, in my experience in Denver, Colorado, drought increases West Nile virus infections in both urban and rural areas surrounding Denver. And yeah, Colorado, definitely there's us here on the East Coast hear a lot about what's going on in Colorado, the West Nile group. So I don't know if you want to have any follow-up to that, Kara.
No, that's a great point. Thank you for sharing, Mel. I was interpreting the question to mean about other vector-borne disease systems, but my apologies if you were specifically interested in West Nile virus in urban areas. That's a good thing to keep in mind, because that's of course where the most humans are living in a concentrated area, and so understanding the relationships in urban areas is very important because it can lead to the exposure of many humans in a small area.
It's kind of counterintuitive too, right? Like we're taught, empty the containers, and so when you think about drought, people, I'm assuming, are thinking, oh, I'm safer, right? So
Yeah.
it's kind of challenging from a messaging perspective when it's drier, and then
Yeah.
your risk actually is going up.
Right. Yeah, and understanding also that message, the targeted messaging to a particular disease system, because something functioning a certain way with West Nile virus doesn't mean it's functioning that way with a mosquito-borne disease. So
Exactly.
the nuances can be difficult to communicate succinctly and in an informative way that doesn't lead to misconceptions.
Absolutely. Yeah. Fantastic. Well, thank you so much, Kara. This was wonderful. A lot to think about, I think, for folks, and some great resources. So just a reminder for everybody that this will be posted. We will have this, you'll be sent, if you registered, you'll be sent an email with the link. We'll also have this on our website with some additional resources. Hopefully you were all able to grab the links that were posted. And we hope to see you at a future event. So thank you again.
Thanks for having me, Erica, and thank you everyone for your time today.